Here we have a heavy bar inside of a lightweight hoop, and it's going to be released and rolled forward, and we're asked to find the minimum coefficient of friction for this to happen without slipping. A good place to always start is with our free body diagram. We'll have an mg acting at the center of mass here, and we'll call that point G. Down here at this contact point, we'll call that C, and we'll have a normal force acting up there. And we should ask, which way do we think friction will act? To the right or to the left? And if you think about it, the wheel wants to roll forward, and yet we don't show any forces in the x direction yet. So that's one clue that the friction needs to act in this direction. A second way to think about it would be if there were no friction, what would happen to this? And without friction, this would basically drop straight down and the hoop would slip. So this prevents that from slipping. So two ways to look at that. If you had guessed the other direction and you stick with it, you'll just get a negative for the value of that, which indicates that your guess was wrong. So it will fix itself in the long run. That completes our free body diagram, so now we can apply our equations of motion. And please recall that we now have 4 of them. We have one equation, we have one linear equation of Newton's second law, and then we have 3 versions of a moment equation. And there's always a tendency to want to try the sum of the moments about G, because it is one of the simpler ones. In this case, it gets a little bit complicated and doesn't really help us too much. I'll start it and then I'll give up on it. So some of the moments about G will be I, G, alpha, and we need to define some directions, so we'll call that positive, so that'd be x, that would be y, and that'd be moments. And we have then friction times r, that's positive, minus the normal times r on 2, that's going to be negative, equals I g alpha, and Ig is straightforward, it would be 1/12 ml squared. But here's the problem. We've written an equation with 2 unknowns, and we're not involving the one thing that is a given, the mg. And that would be preferable to have that in there, certainly rather than 2 unknowns. Now you might say, but we know friction is mu times n, which will be mu times mg. But we don't really know that for sure. Muy importante! We have no proof that n is going to be mg. So without that proof, we can't say that. And this will still be then 2 unknowns. If we leave it in this form, here we certainly can get a common factor of n, but then you still wouldn't know mu s either. So no matter how we spin this or work this, we're going to have 2 unknowns in that equation, which isn't terrible. If we develop enough other equations, we can come back and substitute here. But often, some of these other moment equations down here will avoid that. Let's see what alternative method we have. So for now, we're going to exclude this one, and that leaves these 2 choices. We could do the moments about C, and we have a choice here of doing it with terms of IA and AA, or IG and AG. And if we look up here, G is going to accelerate. It's going to take off and roll with some kind of components and values. I don't feel like dealing with that cross product term in there. That will exist. This term here, however, should be straightforward. So let's use this version of it. So let's write that out. The sum of the moments about C will be IC alpha plus MRG cross AC. And again, whatever we have here, we need to have there. Those two have to match. That's our way of remembering that. And this RG is always RG with respect to whatever point you're doing your moment about. So that's RG with respect to C. And our point C is down here. And what's nice about this, it's rolling without slipping, which means point C, acceleration of C, is 0. That's the case of a wheel rolling along the ground. That point of contact has no acceleration. And therefore, this whole term drops out, which leaves us with just that. So again, we'll pick the same coordinate frame to define our positives. And the moment about C, down here we lose both N and F. And we keep the one input that we have, which is mg. So we get negative mg r on 2. That's the moment for that. And that's equal to I C alpha. Now we do have to calculate I of C, which will be a little bit of work, but not bad. So the I of C will be 1/12 mr squared, the I about the centroid of the bar, plus m offset distance squared, where this is the offset distance right here. And that r value, r squared, will be big R squared plus r on 2 squared. We're going up and then over here. This will become r squared plus r squared on 4, which will be 5/4 of r squared when we work that out. And that's what this is. So we get 1/12 mr squared plus 5/4 mr squared. Making this a common denominator, we'll multiply the top and bottom by 3, and we'll have 15 plus 1, which will be 16/12 mr squared, which is 4/3 mr squared. So with that, we have the I about point C, and we're able to solve this thing for alpha. So we'll get negative mg r on 2 is 4/3 mr squared alpha. The m's go, and one of the r's goes, which will give us directly that alpha is negative 3g on 8r. And what's nice about choosing to do that moment equation, these are all knowns. So that is the value for alpha. And it's negative because of our convention here. We're saying that counterclockwise is positive, and this hoop is going to roll in a clockwise fashion. So that's what the negative is doing there. Okay, our next step will be to try to relate this normal, the friction force, and mg. And the best way to do that would not be with another moment equation, but let's use Newton's second law. Sum of the forces is mag, and that will relate all these values. So in the x direction, we have agx will equal, and there's only one force, just F. So we get F over m, and it's in that direction. And agy will be, and we're calling up positive, so we'll have n minus mg divided by m. So here's our two equations of motion from Newton's second law. And now our job is to relate these values with alpha, the other thing that we know. So somehow we have to relate these two, and the best way to do that is with a relative acceleration equation, such as a sub g is a sub c plus a sub g with respect to c. A sub g is right here, we know it. A sub c is 0 for this problem, And a sub g with respect to c is going to be some r alpha and r omega squared type, which is what's going to incorporate that. So the relative acceleration equation becomes our next step. So when you're trying to do these, generally we look for a moment that's fairly easy to take first. Second thing will be to do Newton's second law and generate your equations about a sub g. And then the third step is to look for a relative acceleration equation that's manageable that will relate these values. So from here, we know a sub g. We've got an agx here equal to f on m. And we have an agy here equal to n minus mg on m. So those are both known right now. That's 0. It's a fixed point of rotation for that instant. Now this, the acceleration of g with respect to c, let's look at that carefully. Here is the bar with g in the center. And here we are down at point C, the contact point. So that makes g with respect to c here, and we're watching g from there, and it's going to have two possible types of accelerations that we could observe. Notice that that's a fixed length r, it doesn't change. So we could observe an r alpha type acceleration, and we could observe an r omega squared type of acceleration from here. The hoop starts at rest, so there's no r omega squared to worry about, just an r alpha type. So with that, we'd like to break this up into components so that we can relate it to our ag values. So there'd be an x component and a y component from this. And we could call this angle in here theta, and this angle is also theta then. And something interesting happens here. This x component would be r alpha cosine of theta, and the y component would be r alpha sine of theta. But if we look back here, we know that this leg is r, and we know that this length is r over 2, and r cosine of theta would be r. So this becomes r alpha in this direction, and the r times sine of theta down here is big R over 2. R sine of theta is that. So this becomes r over 2 alpha directly. Now that's not an accident. The reason that's happening is that technically here, when we do this r alpha, we're doing r cross alpha. Now we set it up so that it was perpendicular, so we could just write it as r alpha. But in general, if we're doing a cross product like that, we can get the x and y components by doing the lever arms to each of those. So the x component of that would be this distance, r times alpha, and that would give us the x component. And to get the y component, it would be this perpendicular distance here times alpha, and that would give us the y component. And together they become the overall component. So sort of a neat little trick. We can prove it with the algebra, or if we remembered it, we could have done it directly and extrapolated these two values. We can now show what a sub g with respect to c is. We found that it was equal to r alpha in this direction, and in this direction it was equal to 1/2 r alpha. And now we can relate the x's and the y values. So if we relate the x's, we have agx, which is f over m, has to equal r alpha, and alpha is 3g on 8r. Now the reason I'm not bringing this negative down is we already accounted for the alpha moving in the negative direction when we evaluated these two terms over here. So we don't want to bring a negative in and undo that work. If we were doing this generically with no signs, we would just guess alpha to be positive and keep going. And then when we plug it in later, it will turn negative and fix itself. But we chose to do it directly. So we don't need the negative down here. We've already addressed it in this portion of the problem. From here, the r's drop out, and we find that the friction force F will be 3 mg on 8. Now, it might be tempting, but you can't say that 3/8 is mu and then that's some mu mg, because technically it's mu n, and we haven't found n yet. And n may or may not be mg, we don't know. There are certainly accelerations in the y direction at play here, so let's wait before we make that kind of an assumption. In the y direction, we have agy, which is n minus mg over m, and that's equal to a negative. Now these are opposites to each other, so we have to put a negative in here. So that's equal to negative 1/2 r, and alpha is 3g on 8r, and the r's go. We can bring this m over to here, and n therefore will be mg minus 3/16 of mg, which will be 13/16 of mg when we evaluate it. So n is actually less than mg. So our assumption would not have been good. However, now we can put these pieces all together. So mu will be F over n, which will be 3/8 of mg over 13/16 of mg. And we'll finally get a mu value of 6/13 when we evaluate that, which is about 0.46 for that configuration. So here's a classic problem showing all the steps and the pitfalls to avoid, such as assuming that that is 3/8 of mg. Mu is not 3/8. We have to carry that calculation further and solve for the normal, which turns out to be less than the weight. And that's because the center of gravity is accelerating downward. Thanks for watching.